What's up, guys? This is Mr. Carlson, C-Squared Mathematics. Welcome back to Algebra 2.1, where we are going to finish our Unit 3, Quadratics. So this week is primarily going to be on graphing and how we relate the function, the actual equation, to the graph. So last week we did primarily all solving quadratics, seeing where the graph actually crosses the x-axis. That was our solution. That was our x equals. Now this week we're going to see the graphs, actually graph them, but we're also going to be looking at domain and range, so that's going to come back. And on the third day, the third lesson this week, our very, very last lesson of Algebra 2.1, our third lesson this week, that last lesson, that's going to be on what if we're given a graph? What if we're given points? How can we actually find the equation of the graph just by giving points, just by giving us points? So a lot of stuff happening this week. Let's get started on the bell work. I have 6 questions total, and I'm going to probably move through them moderately fast because I don't want this video to be too long. But these questions will be, well, they were on your Solve Quadratics quiz. So these are questions that are taken directly from your Solving Quadratics quiz. And so, yeah, these are the most missed questions. So go ahead and pause the screen, at least for these 3, and then we'll get started on the next 3 later. So this one, solve the quadratic using the method of your choice. You could use quadratic formula. You could use factoring. If you could factor it, obviously you could use completing the square. It does not matter. I'm personally going to be using the quadratic formula, okay, only because it's the easiest, I think, and most students don't really have a hard time using the quadratic formula like they do for completing the square. So that's what I will be doing, and this is the formula up here, okay? All right, so obviously my A is just one here, so if we want to label our values, my A is 1, my B is -4, and then my C value is 13. So as I start going through this, you're going to start seeing something very interesting. Well, first, I'm not going to factor it because there's no factors of 13 besides 1 and 13. And obviously 1 and 13 do not add up to -4 or subtract to -4. So I can't factor this beast. I need to do something different, and so that's why I chose the quadratic formula. So x equals, let me find out what these x's are. My b is -4, so that means it's going to be -4, just like this, plus or minus radical. I'm going to put -4 into my parentheses here because that's b squared, following my formula, minus 4, following my formula. My a is 1, and then my c is 13. And then this is all over 2 times 1 because that's my a value, okay? As I start to simplify this out, this is just +4 plus or minus. This is 16. And then -4 times 13, that's just going to be -52. And you'll start to see this interesting thing here. Inside the radical, what will it simplify out to be? A positive? No, it's going to be a negative, which means this is imaginary. If it's negative underneath this radical here, if it's negative underneath that radical, that means it's going to be imaginary. So you couldn't have factored it out regardless. Okay, you could still do the Pythagorean, or not Pythagorean theorem. You can still do the completing the square, but you cannot factor this out. So let's start simplifying. This is plus or minus 16 minus 52 is -36, and then all over 2. I'm going to take out this I, but also notice 36 is a perfect square, so this is 4 plus or minus 6i, and then all over 2. Okay, so when I simplify all this out, both terms can be divisible by 2, so this is 2 plus or minus 3i. This is my final answer. If I went to put this on, technically, sorry, this should be y equals, because all of the equations were y. So technically this should be y equals, but it doesn't matter. It's basically just the quadratic graph. If I went to the Desmos, which I will in a little bit, you're going to see something very particular where it doesn't cross the x-axis. So I'm going to go here to Desmos. Let's actually, I'm going to show you specifically what's happening here. Okay, so I'm going to type this in. So my A is just going to be 1. And then my B was -4. And then this was 13. Okay, so notice how right here, it's already undefined. The reason why it's undefined is because there's going to be negatives in the radical. If I zoom out, I see that I still have a graph, yes, but does it cross the x-axis? No, it does not cross the x-axis, and that's the point. It shouldn't be crossing the x-axis because it doesn't cross the x-axis. It's imaginary. So whenever you get a graph where it doesn't cross the x-axis, such as this, it's therefore going to be imaginary. Okay, does that make sense? Awesome. Awesome, awesome. So let's move on. I'm going to erase this. So actually, I'm going to leave this up just for a little. These I can actually do this next one here. Let's do it in blue. First thing I would do here is factor out a GCF. Every single term is divisible by 3, so I'm going to factor out a 3. And so that's 3, and this is x squared plus 5x, and then plus 6. And now in parentheses, what I can do is actually factor more. This is x plus 3, and then in parentheses, x plus 2. Because what are factors of 6 that somehow, some way add up to 5? Well, there's a couple factors of 6, but 2 of them being 3 and 2, they add up to 5. So this is my final answer for the second one. Okay, very simple. A lot of you, I think, may have even put -3 and -2 for that because you may have thought that this was an equal sign and you probably just plugged it into Desmos and you found your x equals, but you have to read the problem carefully here. The problem says factor the trinomial completely. It does not say solve the equation. Okay, it just says factor the trinomial. It does not say solve the equation. Remember, this is an expression. It does not have an equal 0 at all. This is an expression, so you have to solve it like an expression. Okay, same thing with all other factor trinomials or something like that. If it says solve, however, though, that's going to be the equal sign. You do need to solve it and say what does this x, or in this case y, equal, and it does equal this. Okay, let's go to the next one and then we will move on. So this is solve the equation by the square root property. So I do need to divide this by 2 first before I even solve it. So that goes poofy. I'm left with x plus 9, and then this is squared equals 12. After I get this, I can then square root both sides, square root both sides. This equals x plus 9 equals plus or minus. Now this can be broken up, and this is why maybe some of you did not get this correctly. This can be broken up into 3 and then 4, and then 4 can be broken up into 2 and 2. Since it's a square root, remember I can circle the 2's and they go outside. But what I'm left with is this 3 here, so this is radical 3. So let's, what is happening here? Let's move on over to this side. And so now all I have to do is just subtract the 9 over on both sides. That goes poofy, and I'm left with x equals -9, and then plus or minus 2 radical 3. That is my final answer. Okay, so that one is not too difficult. It's just the square root property. I'm pretty sure that some of you looking at maybe some of your answers, some of you probably multiplied the x plus 9 all the way out. You could do that and you would still get the exact same answer if you did that. You would just, it would not be factorable and you'd have to use the quadratic formula there. But why would you want to do that when you can just divide by 2 and then square root both sides like I did here, simplify the radical, and then boom, you get your answer. Again, if you plug that into Desmos, if you FOILed it all out, you plugged it into Desmos, it would give you a decimal, sure, but that wouldn't be a coherent decimal. You would not be able to transfer that decimal to a fraction because the decimal is a radical. Okay, awesome. So let's erase this and let's go on to our last three questions here. This first one is again factor completely. It does not say to solve. Okay, so I'm not going to solve it. I'm not going to ask what x equals. I'm just going to factor it like I normally would without any equal sign. So I notice that both of these are actually perfect squares. But before I do that, I can take out a couple things. Okay, for instance, I can take out, I can take out a 2 for one, but also a 4. So let's take out a 4y squared. If I take out a 4y squared, what this is going to equal is 16, and then this is y squared, and then minus, if I take out 4 here, this is 9. So I get this. Okay, I notice I can GCF factor that, and both of them have a 4y squared in them. Now I notice that inside the parentheses, it's also another perfect square. So I can square root both of those. So this, if I square root that, that would be another 4y and then minus 3. But because these are perfect squares, and even this right here inside the parentheses, this is what we call a difference of 2 squares. So I'll kind of abbreviate there, a difference of 2 squares. And the reason why it's a difference of 2 squares is because there's a subtraction sign. And I noticed that because it's a subtraction sign and both of these values are perfect squares, that's what makes it a difference of perfect squares. But the way I factor this out is I also need to add in the plus side. Okay, I can't just leave it with the subtraction here because if I FOIL that out, I don't get this. Okay, but if I FOILed this out now, if I FOILed this out in parentheses and I distributed that 4y squared, I would get my original back. So that means this is my final answer. Remember, you can always check your answer. Some of you are just guessing. Why? When you can freaking check it. You have the answer there right in front of you. If all you have to do is just FOIL it back out or distribute it, if you get the original answer back, then you did it right. If you didn't, then you did it wrong. Okay? And so you have to change it, change your factoring somehow. All right? So that's that one. The next one, solve the equation by the method of your choice. In this case, some of you probably have just set it equal to 0 right here and there. You can't actually. You need to FOIL this out. And then you need to add the 1 over. So when I FOIL this out, what I get, let's do this actually in purple here. When I FOIL this out, the first terms, 5x times x is 5x squared. 5x times 2 is plus 10x. 1 times x is just plus x. And then 1 times 2 is just plus 2. Equals negative 1. Okay, let's combine these, and I'm actually going to add that 1 over so I can get 0 on that side. So this is 5x squared plus 11x, and this is going to be plus 3 equals 0. Okay, now since the leading coefficient is not 1, I'm going to actually try to do the divide and slide on this. And so the divide and slide says I'm going to circle these two numbers, the first and last number. 5 times 3 gives me 15. What are factors of 15 that somehow, some way add up to 11? If there are no factors of 15 that somehow, some way add up to 11, then I cannot factor it, which means I would have to use either the quadratic formula or the completing the square. Okay? So I noticed that the only factors of 15 are really 3 and 5, and then 15 and 1. Okay, those are the only factors of 15. So there's no way I can get to 11 there. That's the problem, which means I'm going to actually erase that because I cannot solve it that way. I need to solve it using the quadratic formula. Okay? So my A in this case is 5. My B in this case is 11. And then my C is 3. So let's go ahead and plug it into the quadratic formula. Since it's not factorable, I'm not even going to attempt to plug it in here because if it was factorable, it would be able to show me like fractions and everything. But since it's not factorable, even if I did plug it in here, it wouldn't be coherent. It would just probably give me decimals or undefined because it could be imaginary here. So let's try it. This is x equals. That's x equals, and then this will be negative 11 plus or minus radical. 11 squared is 121, and then this is minus 4. My a is 5, and my c is 3. So I'm going to multiply that out in a little bit. And then 2 times a, so 2 times 5 is going to be 10. So that's what that looks like. This is negative 11 plus or minus. And then I'm actually going to simplify everything in here for right now. So I'm just doing it really quick on my calculator, and I get 61. So it is 61. So it's not imaginary because it's positive. So I literally just did 121 minus 420 minus 4 times 5 times 3, just like you see here. I just did it on my calculator real quick, and that's what I get. Not too bad, right? Yes? And then I get 61. All right, so I get 61, and this is all over 10. So clearly, I cannot really do anything more than this. Why can't I do anything more than this? The reason why I can't do anything more than this is because 61, I can't divide. 61 is a prime number. I can't divide 61 by anything other than 61 itself and 1. So that makes it a prime number, and I can't simplify anything more. I can't divide the 11 by a 10 or a 10 by 11. I can't simplify that radical, so I'm done. Like, that's my final answer. And of course, this is why it wasn't factorable, because it gave me a radical here. So you could do the completing the square, but that would be really nasty. Completing the square would be really, really gross, and I think it would be way easier to use a quadratic formula here, which is why I did it. All right, this last one, they do want you to solve it using completing the square. Now, you don't have to. I don't care if you do. I am personally going to solve it using completing the square. And so I'm going to actually erase all this, and then we're going to get to this example. So I'm just going to bring this up so I have a little bit more room. So x squared minus 6x and then equals 1. How I complete the square is I'm going to set up my basic template here and do a plus blank. This is equal 1 and then a plus blank. So this right here, I take negative 6 and I divide it by 2 and I square that. That equals negative 3, and then I square that to be 9. That 9 is what I put in the blank. Okay. Could you solve this using the quadratic formula? Well, yes, of course. You could solve it using the quadratic formula. I'm just not going to. Okay, I'm going to solve it using completing the square. So that 9 goes in what's inside the blanks here. Because what I do to one side, I do to the other. And I need to make sure the blank. That's what completing the square is about. I'm really completing the actual perfect square here. Because now this little thing right here in parentheses, I can factor that to be just x minus 3 and then squared. That's what I did. I basically completed that perfect square. This equals 8. Sorry, not 8. It equals 10 on the right side, because 1 plus 9 equals 10. I just square root both sides, so this equals x minus 3, and then this is plus or minus square root 10. I can't simplify that 10 anymore because it's just 5 and 2, and that's not, there's no perfect squares I can simplify with 5 and 2, they're prime numbers. And then I just add the 3 over, so I add the 3 over plus or minus radical 10. This is my final answer. Okay? Perfect. Done. Okay? So it is that simple. You don't even necessarily need Desmos. Honest, a lot of these questions I put on here because they're questions that you don't, that you really can't solve using Desmos, and they're the radical type questions. And so these are really helpful questions to go over. We will continue to go over these throughout the next couple days. Okay? So this graph crosses the x-axis at that solution. And that solution, of course, is like a decimal. Let's actually get into our lesson today. It's going to be part 1 because we're going to be spending today just using transformations and then looking at what we call vertex form. That's what today is about. And then tomorrow is going to be about standard form and then the intercepts. So kind of connecting everything together. And then our last lesson of Algebra 2.1 is kind of moderately difficult, but I'm going to show you on Desmos an easy way to do it, and then it'll be perfectly fine. Okay? So today, how can I graph quadratic equations? I'm going to add to that with that essential question. How can I graph quadratic equations? By transformations and by using vertex form. I could add that. Okay? So let's get started into it. This is what we call the parent graph of all quadratic equations. I'm going to graph it here for you, but it is just x squared. Okay, so if I say y equals x squared or f of x equals x squared, this is just your basic parent graph, and we're going to graph it here. So let's go to town on this. If I plug in -3, if I plug in -3 inside of this x, what I get is really just -3 squared, which equals 9. Notice how I put it in parentheses? You need to make sure you put it in parentheses. So it's 9. If I plug in -2, because I'm really looking at this piece, okay? I'm looking at that piece. If I plug in -2, and then I square that, I get 4. Don't get confused with the f of x. The f of x, remember, just stands for function. Okay, that's all it means. It stands for function. A more formal notation is if I plug in -1 and then it looks like this. Okay, that's the more formal notation. And so that means f of -1 equals 1 because -1 squared is just 1. Okay, this again is a point. Notice how this -1 is your x and your 1 is your y. This is a point right here, just like in ordered paired what I have on the table. So just a preview, or not really a preview, it's more like a review of function notation. Don't get confused about that, okay? Let's start going to town. If I plug 0 in here, I get 0. If I plug 1 in there, I get 1. 2 squared is just 4, and 3 squared is 9. So you kind of see almost like, I don't know, a symmetrical nature about these numbers, especially the y numbers, okay? You almost see a symmetrical nature here, and it's very interesting, I think. You get 9, 4, 1, 0, and then 1, 4, 9. So let's start plugging these points in. -3, 9. So I'm going to go to -3 right here, and then 9. I'm going to plot my point. Okay? -2, 4. So -2, 4. Plot my point. -1, 1. It's going to be right here. 0, 0. And then 1, 1. Start to see what's happening here. And then 2, 4. And then 3, 9. Okay? So this is what it looks like. And when we graph it, it looks something similar to that. Okay? And of course, I'm going to put the arrows on top because it does go up forever. All right? But this is sort of what it looks like. I know it's kind of a little bit janky because I don't know how to draw apparently. But that's what my parent graph function looks like. All other quadratic graphs come from this one parent graph. Okay, but let's start, before we move on, let's start answering a couple questions here. Let's find the domain. Let's find my range. Okay, let's find x-intercepts. Heck, let's find y-intercepts as well. Let's find y-intercepts. And then let's find what we call my vertex. I'm going to explain more about that in a little bit. My vertex, my actual point. And then let's see if this is a min or max. Okay? And then at specifically what point is that a min or max? Okay? So let's answer all this stuff. My domain, what is my domain? Remember, domain goes left to right, okay, for domain. So I'm reading it like a book, left to right. So all of these x values is what I'm interested in, all these x values. Why? Because domain corresponds with my x. And if this continues up forever and ever and ever, and this continues to kind of lean towards that way, will I always have an x value that can be attached to my y graph? Will I always have an x value that will eventually meet up with this graph? And the answer is yes. I can always take this x value and just straight up plug it into my equation, and I will always get a number out. No matter what this x number is, I can plug in 1 million in here. I will always get a number out that will eventually line up with my graph as it continues on forever. I can plug in -8, -6. I can plug in 0, of course. I can plug in 10. So all of these numbers I can plug in and I can get a number out. Eventually, this graph right here will go on forever and ever and ever and ever and ever. And this side will also go on forever and ever and ever and ever and ever. Okay, it will continue going up and kind of spread over and over and over and over again until it can't be spread anymore. In this case, if that's the case, it will be -infinity to +infinity. Or sometimes you'll see what we call all real numbers. So that's that symbol, all real numbers. It's like a fancy looking R, okay? But that's what all real numbers looks like. But that's my domain. Now, I will be very, very clear with you. Are you ready? This is, I try to be as clear as possible. When MathXL asks you for the domain of a quadratic graph, it will always, 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 always be -infinity to +infinity. Do you understand? If you graph a quadratic equation, if it asks you for the domain, it will always, always be -infinity to +infinity. It will never, ever, 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 never, ever, never, ever be otherwise. It will always, 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 always be -infinity to +infinity for quadratics. It will always be all real numbers. Do you understand? That's an easy answer that you could get right if they ask you that. Now for domain, that's what it is. For range, it's going to be a little different. It depends on the graph for the range. So it depends because range is not left to right. Range is bottoms up. So instead of going left to right for domain, for range, we're looking at bottoms up because we're looking at my y graph now, my y-axis specifically. So we're basically asking, where does this graph exist on my xy plane with my range? Well, it doesn't start existing until which y value? Okay, this is -2, this is -1. This is what y value? Where does it start existing? Well, it starts existing at -1. No. It starts existing at 0. Yes. Okay. So the reason why it starts existing at 0 is because it's equal right here. The graph actually starts right there at that solution, 0. Now, I'm going to put a bracket here because it's equal to. Why did I put a bracket here for -infinity to +infinity? You can never equal -infinity to +infinity. You can never actually equal that. But it approaches -infinity to +infinity. So we use parentheses. But here, I can actually equal 0. I can see where the graph actually hits 0. So it's bracket. Now, where, as I continue to go up, does it ever stop existing? No. So, comma, it goes to +infinity. Can you ever equal infinity? No. So it's just infinity here. Now, sometimes on MathXL, you're going to be asked to be given a set notation, and it'll look something like this. I'm going to use y because y corresponds with my range, and I'm looking at my y-axis here. So y such that, that's what that line means, such that. So the set of all y such that y is greater than or equal to 0. So sometimes you'll see something like this, and that's what we call set notation. Whereas this right here that I'm boxing, that is what we call interval notation. There's a difference. So interval notation, and this is technically set notation. Okay, that was really the hardest part here. So now let's get to our x-intercepts. It does cross at x equals 0, and this y-intercept does cross at, not y equals 0, silly me. Crosses at y, or x, not x equals 0, crosses at y equals 0. So y equals 0. My vertex is, therefore, of course, 0, 0. And then is this a min or a max? This is actually a min because it's a minimum value here, okay? The max kind of goes on forever and ever and ever. I can never pinpoint the max. So I want a point that I can actually pinpoint, hence the word pinpoint. And that min is right here in purple. So this right here in purple, you can kind of see it right there. That right there, that's my minimum point. And that minimum point is just my vertex, 0, 0. But it's at y equals 0, okay? It's a minimum at y equals 0. That's kind of how we read it. And I'm going to explain more about that later. So this is just the basic foundations for our quadratic graphs. So let's get into transforming quadratic graphs. I'm going to go through a lot of slides pretty quickly, and then we're going to kind of see how each of these transformations relates to each other. Could you technically use Desmos on these transformations? Well, yes, you technically could use Desmos for these transformations. Absolutely. I'm not going to, though. I'm going to show you because it's almost a waste of time. It's so much easier to just use your knowledge of transformations to graph this graph. That's it. So our first transformation is what we call vertical shift. That happens when a number is added or subtracted from the function. Okay, so it causes the function to vertically shift or move up and down. What will that look like? So it will look something like this. This, you don't necessarily need to copy it all down, but this is very, very important. So for this first one right here, what if I have y equals f of x plus c? I'm just going to label it. This would be similar to saying x squared and then plus 7. Okay, so this c, in this case, this plus c, that's 7. It raises the graph up. So when c is added to my actual x squared function. Okay, so briefly what this would look like is something like this. Okay, where that point right here, that's 7. So it kind of just raise it up. And since it would raise it up, this right here is actually imaginary. If I wanted to solve that graph's equations or solve that graph's x-intercepts, I can't because it's imaginary. Well, I can, but they're imaginary x-intercepts. They're not any real x-intercepts because notice if I raise it up 7, it's not touching the x-axis. Okay, it's not touching the x-axis. Now here, if I wanted to do this one, subtract, what that one says, guys, for number 2, it's similar to saying y equals x squared and then like minus 2. So what if I had something like that? Well, that means I would just straight up take this graph and minus it 2 down here. And it would go something like this. So that would be negative 2. Now this does have a an x-intercept. It does have an x-intercept. I could set this equal to 0, and I could add the 2 over. And so this x-intercept is actually plus or minus radical 2. That's where it hits the x-axis, right here and then right here. Okay? So just kind of take those transformations and relate them to our graphs, how we're actually working through our graphs right now. So that's vertical shift. Let's go through our example. So really, really quick. I'm given this, use transformations. If I'm saying x squared minus 4, okay, well, that means this minus 4, that means it moves down 4. So my basic parent graph looks something like this. I'm just going to kind of briefly graph it. My basic parent graph looks something like this. This is where we graphed it in the very first slide. It looks something like that. Now, if I want down 4, I would just take each one of these points, that point, that point, that point, that point, that point, and I would move everything down 4. So that means this point down 4, this point down 4, that point down 4, this point down 4, and that point down 4. So it looks something like that. Okay, and then of course, I can graph it as such. So in red here, that is my actual equation. Okay. Now this shouldn't be a surprise because look at this graph. It's x squared minus 4. I can actually split that up in x minus 2 and then x plus 2. This is a difference of 2 squares. Or I can say equals 0 and then x squared minus 4. I can add the 4 over x squared, square root, plus or minus 2x, right? Or I can just say this, it's a difference of squares, and I can say that, and so x equals still plus or minus 2, because I just set each one equal to 0 here. I mean, either way you do it, whether you use difference of squares or whether you use the square root property, you still get plus or minus 2 for where your graph crosses the x-axis. And what do you know? It crosses the x-axis at plus and minus 2. Okay, so again, try to make those correlations between the graphing them, and actually what we learned about solving the equations before, finding my x-intercepts and all that. Let's erase. Let's go to horizontal shifts or translations. So this is what happens when the number is added or subtracted from the variable of the function. So it's like inside of the function now. It's not like outside of the function at all. This is what we call horizontally shift or move left or right. So I'm given this. So notice how it's not plus c outside here. It's actually kind of attached to my x value inside the function. So what will this look like? Well, this first one will look something like this. Y equals x plus 3 squared. That's what that one would look like. As a brief graph, what it would look like, be very cautious here, it would look something like this. Now, you may be wondering, and this is actually negative 3. So you may be wondering, well, that's a negative 3, but this is a positive 3, Mr. Carlson. Are you insane? No, I'm not. Shift the graph of f left. So shift it to the left. Why is that the case? Because what this is it actually is a built-in negative. I'm going to show you that when we look at vertex form. But vertex form technically is like a built-in negative here. Okay, so this is like my actual graph. Let's just say C is my number. Well, this negative is built in. So if I have a negative 3, what it technically is saying is this, negative 3 squared. So this is why I have in red here. But a negative times another negative gives me a positive. So that's what you see. You only see the positive values. Okay, you only see the positive values there because it's positive. But what you don't see is that it's technically a minus a negative 3. So I take the negative 3 and I move it over. So let's kind of see how that works with this in blue here. What if I have a minus? So this, for second one, this is the same thing as maybe saying x squared minus 4 squared. What will this look like? This will look like something like this. This is 4, and then it would be like that. So then you're asking, well, it's moving to the right now, even though it's a negative? Yes, it moves to the right, okay? Because, again, what it's saying is x built-in negative and then plus 4 squared, okay? I'm going to show, again, more. I'm going to solidify that point when we go to our actual vertex form, when I show you the vertex form, because this is actually very, very important and very, very tricky indeed. But notice how this plus and the negative, that's why I get a negative 4. So this right here, that minus, that's built in. Okay, that's built in. So since it's built in, I don't really worry about it. I just take the opposite sign is what I'm saying. So if this looks like a negative 4, I take the opposite and it's going to be positive 4. So it's going to move it to the right. Okay. If that's a negative, or if that's a positive 3, that means I take the opposite, negative 3, so I'm going to move it to the left. Okay? And that's only true of horizontal shifts. It's not true of vertical shifts. Vertical shifts, it was positive, we moved it up. If it was negative, we moved it down. We did that in the last 2 slides, right? So horizontal shifts are kind of weird like that, where we have to kind of switch up our signs there. And again, when in doubt, if you don't know, you could always plug it into Desmos and just see where it crosses or where it shifts. In fact, we're actually going to be doing that later this week. Okay, so if I'm given something like this, well, this, of course, is just a -2. But remember, it's a built-in negative. So it's the same thing as saying minus a +2 and then squared. So this +2 is going to move up 2. Okay, so if my basic graph looks something like this is my parent graph, right? This is my parent graph. What my actual graph would be is move everything up 2 times. Or sorry, not move up. Wow. Lame. Right. Sorry. It moves to the right. So it moves to the right, not up. My apologies. Getting stuck with the vertical. So if this is my parent graph, it moves everything to the right 2. Okay, because it's +2. So that means all these points move to the right. So that moves, this moves right here, and that moves to the right, and this moves 2 to the right. Okay, so now my actual graph would look something like this. Okay, and again, I'm using it very briefly. I'm not really graphing obviously intensely right here, and I don't need to because Desmos usually covers the base. So I'm just showing you the basic property of what it does. That's all I'm showing you. So it doesn't need to look pretty. I'm sorry, it doesn't look pretty. Okay, let's go through this one. Try to do this one on your own. What do you think it will do? Is it going to move it left, or is it going to move it right? What do you think? Pause the video, and then I'll show you the graph. I'll show you the graph when you come back. All right, so this is what the graph looks like right here. You're just moving it left. So left 4, and then it goes up. Perfect. That's it. Okay, so let's erase that, and let's move on to what we call reflections. So reflection happens when a negative is put in front of the function or the variable. Okay, it causes the function to reflect over the y-axis or the x-axis. Now, mostly we will be focusing on just reflect over the x-axis. We hardly ever will see something when it's reflected over the y-axis because it's not necessarily common, okay? But with all the graphs that we're going to be looking at, we're primarily just going to be looking at the x-axis flips. So what does that look like? Well, if I want to flip over the x-axis, I just put a negative out front. Okay, so let's go through that one first. So basically, your function is just multiplied by -1. So in this case, it would be the same thing as y equals like -x². Okay, and so that will look something like this. So it's just flipped over the x-axis. That's what it looks like. Okay, for this one, for number 2, this is flipped over the y-axis. Now, like I said, we more than likely won't touch on this, but this is what it would look like. So I flip it with a negative and x right here. So that right there is just going to be flipped over the x-axis, or sorry, over the y-axis. So it's really hard to draw, but it basically is just going to be like that. Now, maybe you're wondering, like, that's literally just the parent graph. Yes, it is. It is the parent graph because if I just square this, of course, it's just x². Now, another way to write it is something maybe like this. So -x and then +2 squared. This is going to be a little bit more flipped. So if I actually graph this, this is still going to go to the left, not the right, to the left too. So your actual graph would look something like this. But then I flip it over the y-axis because that's a negative. So then it would be kind of just flipped and it would look something like this. Okay. Again, not necessarily used because most of the time, honestly, I would just divide that by a negative or take a negative out. And so that would become a positive, that would become a minus. And so that -2 means it moves to the right 2. So instead of being at a -2, it would be at the right, a +2. And that's way easier, I think. Excuse me. So that's way easier, I think, to utilize rather than the negative inside of the x. which again, we're more than likely not going to be touching base on that very much. So let's erase that and let's move on to stretch or shrink. Another thing that we're really not going to be touching too much based on is stretching and shrinking, because Desmos is primarily going to be using like basically graphing for us. And so and it's really hard to graph like a stretch or shrink. So for the sake of time, I'm just going to explain it, but I'm not going to necessarily graph it too intensely for you, okay? Because we just don't need to. A stretch and shrink happens when the function or the variable is multiplied by a constant. So it causes this function to stretch or shrink along the x-axis. So in this case, in this one, this c value, this number that's multiplied, is actually greater than 1. So in this example, it would be y equals like 3x squared. This would basically stretch the graph and basically make it fatter. So it would look something like really like this. Okay, it would almost be like a dome. Okay, something like that. Whereas this c, if this is actually going to be in between 0 and 1, so that's an example of that would be like 1/2 x squared. And this would shrink the graph, so that would make it kind of really, really skinny. So it would be something like this. Okay, that's essentially what it would look like. I'm not going to go too much in depth with that because we have a Desmos activity later this week. And that will be useful, yes, and we will be utilizing that, of course, but we're not going to be utilizing it during this lesson. Okay? Awesome. So now let's get to our primary thing, vertex form. What is vertex form? Okay, it's commonly called vertex form because you can actually retrieve your vertex from this form. So it's y equals f of x, which also equals, because y and f of x is the exact same thing, means the exact same thing, equals a times x minus h quantity squared plus k. Okay, this is your vertex form. Maybe you're familiar with geometry in your circles, when you had x minus h and then squared and then plus and then y minus k squared and then equals r squared. Maybe you remember that from geometry, okay? It's very, very similar, of course, as you can tell. Very, very similar. In fact, this is with circles. But even with absolute values, we didn't totally go over this, but we can definitely show you right now. Even with absolute values, I can have y equals a and then x minus h squared. And then I have, actually, no, I'm not going to do squared. Let's not do squared because it's not. Sorry. A times x minus h and then plus k. So even with here, my vertex was still hk. My vertex here is still hk. Okay? That was my vertex. So what do you think your vertex is going to be here with quadratics? It's going to be hk. Okay, A determines the direction and the size of the parabola of the graph, where HK is the vertex of the parabola, where it turns. All right, so that's vitally important. Vitally important. So I will be writing this. Let me actually go back real quick. I'll be writing this commonly. So my vertex, I'll be kind of doing that often, and that is HK. Okay, so I'll be utilizing this formula. So let's go through a variety of examples using the vertex form, pulling out the vertex and actually graphing it. Okay, I'm not going to be utilizing Desmos all that much because we just don't need to. So let's go to town and then we're going to be done. So try to make the connection between absolute values, circles, and quadratic graphs, because really the steps are essentially the same. And the vertex, of course, like I showed you, is essentially the same. So the first step here, when you're actually graphing this, is you're going to determine if the parabola opens up or opens down. Now, if the A is positive, it opens up. If the A is negative, it opens down. That's the reflection part, okay? We went through that already. Find the vertex. That's, of course, just HK. And then we're going to ask the axis of symmetry, what that is. The axis of symmetry, okay? And then we're going to plot the points. and then we're going to find domain and range, and then possibly the min and max. Okay? Awesome. So let's go through this example. Let's go to town. So my first step is to ask if it opens up or down. So what does it open up? Like, is it open up or down? Well, I noticed that this is positive, not a negative. So that means it opens up. Okay? So it does open up. Fantastic. So my second step is to find my vertex, my HK. Remember, my actual formula here, let me write it off to the side. My actual formula is A and then x minus h squared plus k. Now notice the built-in negative. Yes, there's a built-in negative here. So am I going to actually type in for my h -4? No, I'm going to just take 4 because the negative is already built into my formula. So I'm going to take 4 and then my 5 is going to be my k. Notice there's a positive, so I just take whatever sign that is and I just bring it in. So this is my vertex. Let's go ahead and plot that 4, 5. So it's going to be somewhere right around there. Okay? My axis of symmetry. It is literally just x equals, my axis of symmetry is x equals whatever my h value is. My h value is just 4, so I'm just going to bring that down and just say x equals 4. Now notice this is an equation. This is an equation here. Do you understand? An equation, which means as an equation, you must, on Math Excel, type it as an equation. This equation looks something like this. Now I'm going to do it undotted so I can still graph my function, but that's where my axis of symmetry is. That means it's going to flip and be symmetrical on both sides of that line here. Okay? You must put x equals 4. You must put x equals something. You cannot just say 4. That's not correct. It wants an equation. Do you understand? Okay, let's get it right the first time. 4, of course, is just going to be to plot points. So here, you can honestly just do this on Desmos, but I'm just going to plot the basic points from my parent graph. I just go over, up 1, and then over 2 and up 4. So 1, 2, 3, 4. These are just the basic points for my parent graph. That's where I'm getting them. Basic points for my parent graph. And honestly, you don't even really need to know that too much because as long as you know where your vertex is, you pretty much know which quadrant it's in, and then you're going to be fine. And of course, you can use Desmos whenever you need to. Okay, so that's 4. Very, very simple. That's what my graph looks like. Now let's find my domain and range. For domain, it is always, 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 always going to be negative infinity to positive infinity. Notice the negative comes first and then the positive. And I'm looking at it from left to right. If, of course, you wanted to put this in set notation, you could, and it's just all real numbers. Sometimes it's actually listed as the set of all x such that x is a real number. And so sometimes it'll look something like that. Just letting you know, this is interval notation. This is set notation. If I want to find my range, okay, I notice where the graph exists going from bottoms up, right? So I notice it starts existing right here at that y value, at this y value. This is 5. So since that is 5, I'm going to use brackets because it does exist at 5 here. That's what the point is. And then it goes up forever and ever and ever, positive infinity, parentheses. And then, of course, if I wanted to put it in set notation, this is y such that y is greater than or equal to 5. Okay, so that's what it would look like in set notation. These little squigglies are kind of like your braces. So if on your keyboard, it's right by the letter P and right above your enter. So if you do shift and then the bracket, those little things by P, it's kind of looks like parentheses, but it's not. That will give you your brace. What that is, it's a little squiggly line. It actually looks a little bit more formally like that. Okay, it's just a brace. It's different than a bracket. Okay. Now let's look at min or max. Is this a min or max? Well, it is a min because the minimum is right here. But what is that? It is a min at what x value? It's a min at, man, that's an awful at symbol. It's a min at x equals 4. Okay, so at x equals 4, it is a minimum value. All right, at x equals 4 is the minimum value. So you basically say something along those lines. All right, perfect. Awesome. Let's go to another example and let's start just hashing these out. Because they're probably going to ask you, like I said, all these things, specifically the minimum and domain and range. You need to know the domain and range and how to actually calculate this stuff. This is stuff that Desmos cannot help us. Yes, Desmos gives us the graph, but doesn't give us the whether or not it opens up or down. We have to determine that. It doesn't give us the min or the max, and it doesn't give us the domain and range. Okay. It does give us the axis of symmetry, especially if you're using this, but I'm not going to show you that until probably tomorrow. Okay. Let's erase. Let's go through this one. Notice how this one has a 3 here, but it doesn't matter because, again, that means it's going to be fat. Like the graph is going to be a little bit fatter than normal, but that's okay. It's not going to be too big of a deal. Okay. So again, we're just not going to use it. Just know that the 3 will basically shrink it. It'll make it skinny. So that 3 will make it skinny. It'll be kind of really tight. Okay, just know that. That's all you need to know. All right, let's go to town on number 1. Since number 1, this is a positive, that means it is going to open up. My A value is positive here, so I know it's going to open up. Fantastic. My vertex, what's my vertex? My vertex is going to be HK. Notice how this is a positive 3. I'm not going to take that positive 3 because there's a built-in negative here that says minus a negative 3. Okay, so I'm not going to take that positive 3. I'm going to take the negative 3 right there. So always take the opposite sign. But when it comes to the K, I don't need to take the opposite sign. Okay, so negative 3 minus 2. Fantastic. So let's go ahead and plot that. So negative 3 and minus 2. Awesome. 3, my axis of symmetry is just x equals my h value, which is negative 3. Notice how this is an equation. So this is an equation that looks something like this. Awesome. 4, let's plot the points. They're going to be a little bit different because this is going to be basically shrinking it. So I'm really not going to I'm not going to really plot any point here. It's just going to look something like this. It's going to look a little bit tighter than normal. Okay, that's, sorry, not like that. Man, what am I doing? I'm going down. Why am I going down? It's just going to look tighter than normal. That's all. So let me erase this. It's going to look something like this. So notice how this is a little bit skinnier than probably our other graphs because that's what that 3 does. The 3 just kind of makes it slightly more skinny. Okay. 5, domain. So domain, of course, is negative infinity, positive infinity. And we can also write that as just all real numbers. My range, what's my range? Bottoms up, right? So where does it start existing? What y value? It starts existing at negative 2, going all the way to positive infinity. Another way to write this is the set of all y's such that y is greater than or equal to negative 2. Okay? Awesome. That's my domain and range. And then my min and max. This is also another min. And where is that at? That's at x equals negative 3. Okay? And so I always want to say the minimum at x equals something. That's kind of the general formula that I do. So it's always going to be minimum or max at x equals some number. All right? Because the min and max tell you the y value already. It basically tells you if the y, if it's being flipped over or flipped down. It's not asking for the actual y value. It's just asking for the min or max. So this counts as technically your y, and this is specifically where on your y's is it at. It's going to be at x equals negative 3. Okay. Let's move on. So try to do this one yourself. I'm going to pause the screen, try to do it, and see if you can get the right answer. It's a little bit tricky because there's a negative here, but that's okay. I think we can do that. If we can do this, then I'm sure you guys can do it yourself. So pause the screen, see if you can get the vertex, axis to symmetry, plot the points, domain and range, so forth. Perfect. It does go down. My vertex is 6, -4, because I had to do the opposite sign here. So this is going to be a +6 instead of a negative. So +6, -4 right here. My axis of symmetry is right here. This thing is x equals 6. So that's where it kind of flip-flops back and forth. That's my axis of symmetry. My domain is, of course, -infinity to +infinity, or what we call all real numbers. My range now, from bottoms up, it does exist from -infinity. Starts existing from -infinity, so that's what I'm going to put there, but stops existing at -4. So that's my y value where it stops existing. So I'm going to do -4 bracket. And so my set notation will look like y, the set of all y's, such that y is less than -4. The set of all y's such that y is less than -4, okay? Because it exists in all these negative numbers that are less than -4, and it doesn't exist above -4. And then, of course, my max, because instead of a min, it's an actual max, and that's at x equals 6, my axis of symmetry there. Sweet. So if you got that correct, good job. You are a master at vertex form. So what did we learn? We learned quite a few things. We learned how to basically recognize parabolas and its essential properties and characteristics. Graph parabolas using transformations in vertex form as well. Okay, make sure you are reviewing your notes. We will have a homework quiz that's optional for tomorrow. The retakes for the Solve Quadratics quiz will be available this week, and it's going to be due next week on Monday. So please email me if you need to retake that quiz. I can open it up for you, and then just be working on your homework just like normal, okay? Until next time, guys, be sure to like and subscribe. This is C Squared Mathematics. See ya.